This video is actually kind of an optional video. It doesn't cover stuff that's necessary to understand the videos coming afterward, but it contains a few interesting and useful concepts that you might want to know for future physics reasons. So let's think about last video. We said the potential energy equals mass times gravity times height. But what about gravity? Is gravity always the same in every single place? In a lot of cases, that seems like yes. Almost anywhere on the surface of the Earth, gravity is about 9.81 meters per second squared. Actually, where I am right now, it's only 9.80 meters per second squared. It does vary slightly, but for the most part, it's very, very constant. And even if you go way up or way down mountains, it still stays pretty much the same. But what if you went all the way into outer space? So you got the Earth down here, the blue planet. We've got a satellite way up here. It's a full Earth radius away from the Earth. Is it experiencing the full force of gravity? Is gravity 9.81 here? Or is it something else? If we want to figure this out, we're going to need an equation for figuring out the force due to gravity. And this equation is actually one of the big discoveries of Newton. And this is the law of universal gravitation. It's that the force between two objects is mass 1 times mass 2 times a gravitational constant divided by the radius squared. So now what is this gravitational constant? Well, this gravitational constant is the thing we need to relate our answers together. We could ignore it, pretend it doesn't exist, and we'd get answers that were consistent with each other. But they wouldn't give us answers in joules. And since all of our other energy and work and power all relates back to joules, we want this to also. So experimentally, because when you're converting between systems, you always have to do experiments to determine what's right and what's not, we determined the gravitational constant is 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. And the meters kilogram second squared part, that's just to get the units to line up right. But let's look at the 10 to the negative 11th part for a second. This is a really small number. That's a decimal point followed by 10 zeros followed by 1. That's ridiculously small. And what this means is it takes a tremendous amount of mass for gravity to do much of anything. That's why the Earth's huge mass is able to pull you down, but not so much that you can't stand up or jump up in the air. And that's why when you go to pick up stuff off the ground, it doesn't fly up and hit you in the face, attracted by your gravitational field. So as a result, this number is going to be really small. So even when we have really big masses, mass 1 or mass 2, we still get reasonable sized answers. So now we have an equation that gives us the amount of force that different things experience at different heights. We can say that the force is mass 1, mass 2, gravity over radius squared. And what's radius squared? Radius squared is the distance between an object, actually the center of the object, and the center of the other object. So if this is our satellite, we notice that this satellite has a much larger radius than we do with the Earth. And as a result, since it's divided by a large radius squared, it's experiencing less force. And now this is going to make our calculations for gravity a little bit tricky. Because see, going back to our old equation, it assumed that gravity was constant, mgh. You can't plug in something that's different at different levels. It's too tricky. Now if you were really hardworking, you could go through and you could do it bit by bit. You could say for the first meter of height, for the second meter of height, for the third meter of height, and calculate gravity at each location. But that wouldn't actually quite work. And it would take a super long amount of time. And even then, you'd still be off by a little bit. So there's a better way to do this. And this is called an integral. And if you've never heard of an integral, don't worry about it. But all that matters for this course is that we can take the integral, we can transform the acceleration, because force over mass is acceleration. So acceleration is mass times gravitational constant over radius squared. And we integrate it to get negative mass times gravitational constant over radius. And this is the potential. Now you probably don't quite understand why this works, and it's a little hard to explain without using calculus. But for the time being, just know, if something's really far away, the potential energy is negative mg over r. Now how do we use that? The way we use this is we plug in two separate r's. First of all, we figure out its potential energy at its ending location, and then at its starting location. So let's not do it with numbers quite yet. Let's just use some constants. let's say out here, the radius is 3 Earth radiuses, 3 times the radius of the Earth, and here it's 1 Earth radius. What's the potential energy? Or the change in potential energy, to be specific? Well, change in potential energy, once again, delta just means change, is negative mass times g over 3r minus negative, so plus mass times g over r. Now let's do some adding of fractions. We end up with negative mg plus 3mg over 3r, which simplifies down quite nicely. We end up with 2mg over 3r. And that's our potential energy. So if you take an object and move it from 1 Earth radius all the way up to 3 Earth radiuses, if you plug in the correct mass and the correct gravity and the correct capital R, that's the radius of the Earth, that's your change in potential energy. And this explains a lot of things. And one of the big things it explains is why this previous formula is negative. Because what you find out is the potential energy at any point is negative. But as you get farther and farther away, it gets less negative. So when you plug in the numbers, it actually comes out as positive, and we actually end up with a positive change in potential energy when we go up, and a negative change in potential energy when we come back down again. So I hope this gave you a little more of an insight into how potential energy works when you get far enough away from the Earth, the distance actually matters. A lot of this you don't actually need to know right now, but it's just a little bit of a taste of some of the more complicated physics to come, and some of the really cool things you can do in physics if you have the more advanced math to deal with it.